We're going to talk about covalent bonding for this last part of Unit 4A. So covalent bonding, hopefully you remember, is made of nonmetals. So these are the things to the right of the stairs. Because we're not talking about Lewis structures just yet, I'm going to try and keep the molecules that we talk about in this section to organic molecules that we have talked about how to draw the structure for. So how does a covalent bond form? And it's when those atoms are sharing electrons. Remember, from metallic, they form that delocalized electrons. When it's ionic, they transfer electrons. Sharing the electron pair allows the nonmetals to achieve that stable octet. Remember, atoms want to be like the noble gases. They want the full valence shell, and so nonmetals will share in order to do that. The shared pair of electrons is what holds the atom together by electrostatic force. Remember, electrostatic force is found in all of our bonds. It's just what is it between. So for metallic, electrostatic forces are between the cations and delocalized electrons. In ionic, the electrostatic force is between the cation and the anion. And for covalent bonds, the electrostatic force is between the nuclei and the shared electrons. So it's this force right here that is holding this bond together. A covalent bond stabilizes when the energy is released to form the bond. And that's kind of what this graph is showing. The forces of attraction between the nuclide and the shared electrons are balanced by the repulsion of the two nuclei. So then the atoms are held a fixed distance apart, and this is where we find our bond length, or the distance between the two nuclei. So when that amount of energy has stabilized, it's found at the bottom of this curve, and that's where we can get the distance between the nuclei, or the bond length. Octet rule. So remember, all atoms want 8 valence electrons so that they have that full outer shell. Lone pairs is the term, so that's the vocabulary we use for electrons not in the bond. So for this chlorine atom, we have the bonded electrons here. The rest of the electrons then would be referred to as lone pairs. There are some exceptions, and in Chem 1, we only talk about hydrogen being the exception. There is more than just hydrogen, though. Some transition metals don't need 8 valence electrons, which is why they can have various charges. Radicals, like we saw in organic, when we had Br with just the dot, when we broke that bromine, or if we take our chlorines here, if we break this bond, they would form 2 chlorine radicals. So that's an exception to the octet rule. And then beryllium only needs 4 electrons to be happy. Hydrogen, we should know from last year, is 2. And then boron only needs 6 electrons to be happy. So hydrogen, beryllium, and boron can have less than 8 and still be stable. And then any element that's in row 3 or lower can break the octet rule by having an expanded octet, meaning they can have more than 8 electrons, and that's because of the d orbitals. Remember, the d sublevel doesn't come into play until you reach the 3rd energy level. So once we have that d sublevel, we can start filling in more than 8 electrons and still be stable. And this is when it starts getting a little more confusing, so make sure you ask questions if you have them. When atoms go to bond together, they have to bond equally. Like you can't have one electron bonding in a p sublevel and another electron bonding in an s sublevel and have it be the same energy in the bond. So what happens is nonmetals will undergo something called hybridization, where they take their valence orbitals and they mash them together so that they're bonding the same type of orbital for all of their bonds. And their lone electrons are also in that same hybridized shape. So if you have four things surrounding an atom, you have four spots, there's either a bond or there's a lone pair, you're going to take your s orbital and your 3p orbitals, so that's 1, 2, 3, 4 spots for these things to be at, mash them together, and we get what's called Sp3 hybridized. So instead of having S, which is spherical, and then your P, which is peanut shaped, they turn into a hybrid where there's similarities of both, which we call Sp3 hybridized. If you only need 3 spots, then you're going to use one S and then 2 P orbitals. We're not going to have a fourth P or a fourth spot or the third P orbital being used. And so we get Sp2 hybridized. If you only need 2 things, then you would have an S and 1 P, and so it becomes Sp hybridized. So let's take a look at how this is worded in a question, or how we determine this. So our example here, what type of hybridization is needed for the carbon in CH4? So hopefully you remember that CH4 is methane. And so we would have carbon and our 4 hydrogens going around the carbon. So it would look like this. So carbon has 1, 2, 3, 4 places that it needs to bond. So it's going to use its 2s and then all 3 of its 2p's in order to create equal orbitals to bond with the hydrogen. So that means the carbon is Sp3 hybridized. It's smushing all of those together to create those equal bonds. All right, if we change it up and we look at C2H2, you have your carbon to carbon, and then each of those would have 2 hydrogens, which means the carbons have to be double bonded. So hopefully you remember then that this would be called ethene because of the double bond. So around both of the carbons, we only have 3 things. We have a hydrogen, and then the carbon. So there's 1, 2, 3 things around. So I don't need all of these orbitals. I just need 3 of those orbitals. So this carbon then becomes Sp2 hybridized. So 2 P's and 1 S to make them all equal. This carbon over here, since it's symmetrical, it's the same thing. It has 2 hydrogens and then the carbon. So it is also Sp2 hybridized. The next one we have is not necessarily an organic compound. It's carbon monoxide. So carbon, remember, having to have 4 bonds, and then our oxygen being the only atom it can bond to, it actually forms a triple bond, because a quadruple bond is not a thing, and then they both have lone pairs on either side of them. So the carbon has 1 lone pair and 1 atom attached. So it has 2 things around it, so it is Sp hybridized. If we look at the oxygen, we can give hybridization for that as well. You have 1 thing attached to it and then 1 lone pair. So it also would be Sp hybridized. So how did those double and triple bonds come into play? So what happens is when the orbitals are overlapping, and these are our hybridized, I didn't spell that right, orbitals, it's called a sigma bond. So this symbol here is sigma. So that's what this green area is showing, is that overlapping hybridized orbitals. When the orbitals are perpendicular, which is what the blue orbitals are showing here and here, that's a pi bond. So the electrons that are held in this non-hybridized orbital are allowed to jump back and forth between them, and that's how you form that double bond. So a single bond is the sigma. The double bond is made of a sigma and a pi. So if you think back to our ethene, which look like this, remember that those carbons were Sp3 hybridized. So 2 of the p orbitals are used to create the overlap, and then we have a non-hybridized p orbital to help us form that second bond. So that's what one of these in the double bond is. Now if you have a triple bond, then you have a sigma and 2 pi bonds. So you would have another set that's rotating down here on the other lobe. So that's like our carbon triple bonded to the oxygen, right? Those are Sp hybridized. So they have 2 p orbitals. So you could even pretend that there's one that's coming out like this, perpendicular here to the screen, and they're allowed to jump back and forth. In sections 10 and 11 of the data booklet, it gives the bond length and the bond strength values. And so those values are given to you. We would not have to calculate those on our own. What you need to remember, though, is that as the bond length increases, the enthalpy, which is the strength, decreases. So the longer the bond, the weaker it is. The shorter the bond, the stronger it is.